All right, let's dive right in. If you're revising for your GCSE chemistry exams, you are in exactly the right place. We're about to do a crash course on atomic structure, which is section 4.1.1 in the AQA spec. Seriously, this stuff is the bedrock of all of chemistry, so if you can nail this, you're looking at a serious grade booster. Ready? Let's go.
I mean, think about it. It's a huge question, right? The screen you're looking at, the air in the room, you. What is it all actually made of when you get down to the tiniest, most fundamental level? Well, that's the question that's driven chemistry for centuries, and that's where we're going to start. Okay, before we can get to all the cool stuff, like understanding chemical reactions, we need to be speaking the same language. So this first bit is all about getting the key definitions locked in. You absolutely have to know these for your exam. Let's get this vocabulary down. First up, the atom. The easiest way to think of it is like a single ultimate Lego brick. It's the smallest possible piece of an element you can have. You can't break it down anymore in a chemical reaction. It's the basic unit of, well, everything. So, if an atom is one Lego brick, an element is just a giant pile of the exact same type of Lego brick. A bar of pure gold, it's made of nothing but gold atoms. A balloon full of helium, nothing but helium atoms. And you'll find every single known element listed on the periodic table, which, by the way, is going to be your best friend in that exam. Now, what happens when you take different types of atoms and chemically stick them together? You get a compound. The classic example is water, H2O. It is always two hydrogen atoms bonded to one oxygen atom. That fixed proportion part is crucial. It's like a strict recipe, and it creates a totally new substance with brand new properties. And that leads us perfectly into a classic exam question. What is the difference between a compound and a mixture? Well, in a compound, like we just said, you've got chemical bonds forming something totally new. But in a mixture, think just stirring salt and sand together, there are no chemical bonds. The bits are just mixed. You can usually separate them easily, and they haven't changed. So the bottom line for your exam, compounds involve a chemical reaction, mixtures don't. So we know what an atom is, but our idea of what an atom actually looks like has changed a ton over the years. And this isn't just a history lesson, by the way. The AQA spec specifically wants you to understand how scientific models change when new evidence comes along. It's kind of like a detective story. So here's how the story unfolds. Way back in the early 1800s, scientists just thought atoms were tiny solid balls. Then, in 1897, the electron was discovered, which led to this idea of the plum pudding model. But then came 1909, and a truly game-changing experiment gave us the nuclear model. A few years later, a scientist named Bohr refined it by putting electrons into specific shells. And finally, in 1932, Chadwick found the neutron, which basically completed the model we use today. Okay, pay close attention here, because this is a direct quote from the AQA spec, which means it's super important. This alpha particle scattering experiment was the big one. Scientists fired these tiny particles at a thin sheet of gold foil, and what happened was shocking. Most particles went straight through. It proved the atom was mostly empty space with a tiny, dense, positive bit in the middle, the nucleus. And just like that, the plum pudding model was toast. So to wrap that up for your exam, you need to know the key differences. The plum pudding model was this idea of a solid ball of positive charge with negative electrons just dotted through it. But the nuclear model, the one that came after the gold foil experiment, says the atom is mostly empty space, with a tiny positive nucleus in the center containing all the mass, and the electrons are on the outside. Okay, so we've got our modern nuclear model. Now it's time to zoom in and figure out what's actually going on inside it. Let's decode the subatomic particles and learn how to read all that info the periodic table gives us. This table right here is pure revision gold. You've just got to memorize it. It's pretty simple, though. In the nucleus, you have protons. They have a mass of 1 and a positive charge of +1. You also have neutrons, which also have a mass of 1, but they're neutral, so 0 charge. Then, whizzing around the outside, you have the electrons. Their mass is so tiny, it's basically 0, and their charge is -1. Right. When you look at the periodic table, you'll see each element written kind of like this. It's a code, and it tells you everything you need to know about its atoms. The big number on top is the mass number, and the smaller number on the bottom is the atomic number. Let's break down what those actually mean. The atomic number is the most important one. You can think of it as the atom's ID card. It tells you the number of protons, and that number is what defines the element. Every single carbon atom in the entire universe has 6 protons. If it had 7, it wouldn't be carbon anymore. It would be nitrogen. It's that simple. And here's the key tip. In a neutral atom, the number of positive protons has to equal the number of negative electrons. So the atomic number actually tells you both.
The mass number is pretty much what it says on the tin. It's the total mass of the atom. And since electrons weigh almost nothing, we find the mass by just adding up the protons and neutrons in the nucleus. So a really common exam question is to find the number of neutrons. All you do is take the big number, the mass number, and subtract the small number, the atomic number. That's it. Easy marks.
Here's an interesting thought. We know that the number of protons is what makes an element an element. But what if you could have an atom of the same element, but with a different number of neutrons? Would that even work? Well, yes, it does. And it creates something really important. And what it creates are called isotopes. Isotopes are just different versions of the same element. They have the same number of protons, so their atomic number is the same, and they react chemically in the exact same way. But they have a different number of neutrons. This means their mass number will be different. Think of them like chemical twins that just have slightly different weights. And this is super useful for things like carbon dating, which uses a special isotope of carbon to figure out how old things are. All right, we're on the home stretch. We've sorted out the nucleus. Now it's time to look at the electrons. Because where they are and how they're arranged, well, that's the key to understanding pretty much all of chemical bonding. This is a practical skill you'll definitely be tested on. First thing to know, electrons aren't just buzzing around the nucleus randomly. They live in specific energy levels, which we call shells. You can think of it like seats in a stadium. The best seats are down at the front, closest to the action. Well, electrons are the same. They always fill up the lowest energy shells, the ones closest to the nucleus, first. And for GCSE, there are some really simple rules for filling these shells. Rule 1, you always start from the inside out, the shell closest to the nucleus. Rule 2, that first shell can only hold a maximum of 2 electrons. Once it's full, you move out to the second shell. Rule 3, the second and third shells can each hold a maximum of 8 electrons. So the pattern you need to remember is just 2, 8, 8. Let's put that into practice with an example. Sodium, its atomic number is 11, which means we have 11 electrons we need to find a home for. So the first 2 go into that first shell. Boom, it's full. We've got 9 left. The next 8 go into the second shell. Okay, now that one's full too. We've used 10 electrons, so we have just 1 left over. That lonely last electron has to go into the third shell all by itself. So the electronic structure for sodium is 2, 8, 1. And that one single electron in sodium's outer shell, it turns out that's the most important part of the whole atom when it comes to reactions. In fact, this whole system of electron shells is the secret to understanding why elements behave the way they do and why the periodic table is laid out the way it is. So that leaves us with a massive question. How does this simple design of the atom manage to explain the entire periodic table? We'll get into that next time. See you then.